Okay, we're going to talk about the fundamental theorem of arithmetic in this presentation. And well, you know that in a proof class you need to follow all the arguments that are presented very carefully so that you understand the proof and so that you get used to the ways of thinking, the habits of mind of a mathematician that does proofs. I request that in this presentation you follow extra carefully, and that is because I'm deviating a bit from Rosen's presentation here, and that in itself isn't that much of a problem, but you see, when I started reading Rosen's book, I immediately thought, man, I'd like to write like that guy. I'd like to be able to write like that. Not because I dislike my own writing style, but because his writing style is very nice, and I would like to have that skill set too, and without shame I can admit that I don't. Okay, so I came to his presentation of the fundamental theorem of arithmetic, and I thought, man, there's got to be a faster way to present the fundamental theorem of arithmetic. And in fact, I have presented it faster in my book on fundamentals of mathematics. Well, when I think that there are two possibilities, either there is a faster way or I'm wrong. And that would be a bit embarrassing because if I have presented that wrong way in a textbook that I wrote by myself, well, that's not good. It turns out that the truth is somewhere in the middle, apparently, because a key lemma that I delegated to being an exercise in my book actually is harder to prove than I thought, but at the same time there is a faster, more direct way to get the fundamental theorem of arithmetic, and that's what I'd like to present to you here. So let's be careful, and if there is a mistake in the proof of that key lemma, please let me know, and well, I'll try to fix it again, or who knows, maybe at some point in time I simply have to admit defeat, and maybe there is just no other way to prove the fundamental theorem of arithmetic than the way that Rosen takes, which builds more machinery, which is not bad because the machinery that he builds is machinery that in fact we will build in the next presentation. But I'd like to pull the fundamental theorem of arithmetic forward because it is fundamental and it ought to have an elementary proof. Okay, let's take a look at it. So, we know that prime numbers are indivisible, and that means it stands to reason that everything else is made up of prime numbers. And to prove this very reasonable idea is surprisingly complicated, as I just mentioned. Once we have proved the fundamental theorem of arithmetic, however, we will also talk about least common multiples and greatest common divisors. We'll show some results, but mainly we also realize that now we can prove that they exist. And we'll talk a little bit about roots of polynomials, namely, a polynomial with integer coefficient and leading coefficient 1 will have roots that are either integers or irrational numbers, but it won't have rational roots, which is kind of interesting. Okay, first lemma is actually fairly simple. If you take a positive integer greater or equal than 2, then there must be a prime number that divides that integer n. The proof is a strong induction on n, and well, basically that means we start in a base case, and the base case is trivial because 2 divides 2, so 2 has a prime number that divides itself. And then we continue how we always do in strong induction. We take a number n that is past the base step, and we assume that the result holds for all applicable numbers before n. Okay, if n is prime, we're home free. We just choose p equals n, and that's it. And if n is not prime, then there are integers k and m that are greater or equal than 2 and strictly less than n, so that n is equal to k times m. And by induction hypothesis, that means there's a prime number that divides k, and of course that prime number divides n too, and that finishes the proof already. So this one wasn't that bad at all. And the next one is the key lemma that I want us to be careful with. If we take two positive integers c and d and p a prime number, if p divides the product c times d, then p ought to divide c or p ought to divide d. Let's think about that. Well, if prime numbers are indivisible, then we can split them between c and d, so it's reasonable, but how do you prove that, right? Just because something is reasonable doesn't mean we have a watertight mathematical proof. And of course, if we already had the fundamental theorem of arithmetic, we could say that p can only occur in if P occurs in a prime factorization, it occurs fully in a prime factorization, but that would be circular reasoning, right? We cannot use the theorem that we want to prove eventually to prove a lemma that we need to use for the theorem. So that's a bit of an impasse, and certainly Rosen resolved that impasse very nicely because he builds a lot of machinery that we will need eventually anyway, and then proves some lemmas that lead up to this one. Let's see if we can do an elementary proof here. So the proof goes as follows. We suppose for a contradiction that the result is false. Well, that means we can find positive integers c and d so that p divides c times d and p divides neither c nor d. And we can also assume that c plus d is as small as possible because remember, for any set of natural numbers, including the natural numbers that are sums of these counterexamples, any of these sets must have a smallest possible entry, right? Okay. So without loss of generality, we can assume that c is less than or equal than d because any two natural numbers, one of them will be less than or equal than the other. And that then leaves us the following possibilities if a is so that a times p is c times d. And of course, if p divides c times d, then there must be such an a, right? But if AP is CD, we've got the following possibilities. We could have that A is strictly smaller than C, less than or equal D, smaller than P, because, well, P is not equal to D and it's not equal to C, otherwise we would not have a counterexample. So D could be greater than P. And, well, when D is greater than P, then A would have to be smaller than C, because A greater or equal than C would give us that AP is strictly greater than CD, and that would contradict the equation here. We could have that A, the other factor, is greater than D, and then basically A and P just switch roles. We could have that P is smaller than D, but greater than C, and that would then mean that A is greater than C, because otherwise, again, we would have, let's see, if A was smaller or equal than C, we would have AP strictly smaller than CD, and that would be wrong. Or we would have that A and P switch roles, and we might as well also assume here that P is strictly smaller than A because equality is already taken care of in case 3. And so, as I mentioned, any other possibility, any other way in which we could line up these numbers leads to AP smaller than CD or AP greater than CD or to a cancellation of A or P. Okay. So now we have to look at these 4 cases, and the first case would be that A is strictly smaller than C, less than or equal than D, smaller than P, and in this case we will choose X and Y so that C is A plus X. And that means in particular that X is smaller than C, right? And we let Y be so that D is equal to P minus Y. And then, well, AP was CD, well, that would mean that CD now is A plus X times P minus Y, and we can multiply that out, so we get A times P minus A times Y plus X times P minus Y. AP cancels, so we get 0 being negative AY plus X times P minus Y, which is negative AY plus X times D here, right? And that means AY is XD. But now we can choose Q to be a prime factor of A, and that would mean that A is equal to Q times U. And because C times D was as small as possible, and that would mean because X is smaller than C that X plus D is smaller than C plus D, because that was as small as possible, we would have that Q divides X because Q divides A, and therefore it also divides X times D. So Q divides X, which means Q divides C, or Q divides D. And so let's just say that C is equal to Q times V. Well, then Q times U times P is A times P, sure, because A is QU. AP was CD, and C is QVD. And now we can cancel the Q, so that means that UP is VD, and cancellation of integers is allowed. That is something that can be proved from first principles. And that means, and moreover, we have that P doesn't divide V because that would mean that P divides C, and P doesn't divide D by assumption. But that contradicts that c plus d was as small as possible, because you see v is a divisor of c, and that means v is smaller than c, and d is of course d, so v plus d would be smaller than c plus d. Okay, that takes care of the first case. The next case is that p is smaller than c, smaller or equal d, smaller than a. We let x, y be so that c is p plus x, and that means that x is smaller than c, and we let y be so that d is a minus y. Well, then again, AP is CD is p plus x times a minus y, and this time we multiply that out like this. We get PA minus PY plus x times a minus y. PA cancels, so we get 0 equals negative PY plus x times a minus y, and that would be XD. Good. And that means PY is XD. And because C plus D was as small as possible, that would mean, because remember x was smaller than C, right? So x plus d is smaller than c plus d. So that means because c plus d was the smallest possible smallest possible size for the sum of a counterexample, that means that p divides x or p divides d. Well, because p doesn't divide d, we must have that p divides x. But p divides x means that p divides c, because if p divides x and p, then p divides c. And that's a contradiction. And the other cases now work exactly like the argument we had before. So if we have c smaller a smaller or equal p smaller d, we take x and y so that c is a minus x, and y so that d is p plus y. And this time y is smaller than d. AP is cd, which is a minus x times p minus y. So that gives us AP minus xp plus a minus x times y is AP. AP cancels, we get negative xp is a minus yx, which is negative xp plus cy. And so that gives us xp equals cy. And remember that y is smaller than d, so c plus y is smaller than c plus d, and because c plus d was as small as possible, p divides c or p divides y. And because p does not divide c, we must have that p divides y, but once p divides y, p must also divide d, so that implies p divides d, and that's a contradiction. And finally, if c is smaller, p is smaller than a, is smaller than d, we take x and y to be so that c is a minus x, y so that d is p plus y, again y is smaller than d. And then AP is cd, which is a minus x times p plus y, and that means that AP is AP minus xp plus a minus x times y. AP cancels, so that gives you 0 equals negative xp plus a minus x times y. Well, a minus x was c, so this is negative xp plus cy, and so xp equals cy. And again, because y is smaller than d, c plus y is smaller than c plus d, and c plus d was the smallest sum for a counterexample, and so that means that p divides c or p divides y. P does not divide c, so p must divide y. And that implies that p divides d, and that's a contradiction. And that's the end of the proof, because we have shown that every single case leads to a contradiction. Okay, so this direct proof was a bit more complicated than I expected it to be. If this proof were presented in a text after the second case, people would say the other two cases are similar and leave that as an exercise. Because I'm right now a little bit worried as to whether my argument fully holds water, I presented it all. Follow it carefully, check the details. That is not something that is bad for you. A lot of learning mathematics ultimately is about gaining the ability to check details of somebody else so that ultimately you can check your own details. And once you have done that, let's move on, because for the rest of this presentation I am, well, heartily unworried about the arguments, because they're all rather standard arguments. Let's get to them, but let's also make sure that you see them correctly. So we're now going to prove a generalization of this little lemma, and that is if you've got n positive integers and p a prime number, if p divides the product of these numbers, then there must be one number, there must be ni, so that p divides ai, so that p divides one of those numbers. The proof is fairly simple because it's an induction on n, on the number of factors. Well, for n equals 2, it's that lemma that we've just proved. And for the induction step n to n plus 1, Well, if p divides the product a1 to an and an plus 1, well, then we just bracket that, right? Because then p divides the product of the first n numbers with the n plus first number. And by the previous lemma, that means that p either divides the product of the first n numbers or the n plus first number, or even both. And by induction hypothesis, that means, well, either p divides an plus 1, or by induction hypothesis, p divides one of the aj's with j smaller than n. And so overall, that means p divides aj for some j between 1 and n plus 1. And that's what we wanted to prove. Now we get to the fundamental theorem of arithmetic, which is about the existence and uniqueness of a prime factorization. It is called the fundamental theorem of arithmetic, or it is also sometimes called the unique factorization theorem. And, well, we take a natural number n, then either n is equal to 1, or there are unique distinct prime numbers p1 through pk, and not necessarily distinct exponents q1 through qk in the natural numbers, so that n is the product j equals 1 to k pj to q to the j. So that is basically that n factors into a bunch of prime numbers, and we can sort those prime numbers so that every prime number only occurs once as a prime power. First, we prove that there exists such a factorization. Remember, anytime you've got an existence and uniqueness result, you often first prove existence, then you prove uniqueness, or vice versa. And so here we're using strong induction on n. The base step n equals 1 is trivial because we have n equals 1 as a separate case. For the induction step, you take n to be a natural number. If n is prime, you choose k equals 1, p1 equals n, q1 equals 1, and you're done. And if n is composite, then by our first lemma, there is a prime number p, so that n is equal to m times p, where m is between 2 and n minus 1. And that means by induction hypothesis, there are prime numbers p1 through pk and exponents q1 through qk, so that m is the product j equals 1 to k pj to the qj, where the pj's are distinct, and hence n is equal to p times the product j equals 1 to k pj to the qj, and it's just a matter of sorting things. The extra factor p is either equal to some pj, in which case we add 1 to the exponent qj, or it is not, in which case we set pk plus 1 equal to p and qk plus 1 equal to 1. And in either case, we are done. Okay, so existence is given. We also want to have uniqueness. We want to make sure that basically the only thing that could happen is that the order of the factors gets scrambled. And to do that, well, we again use strong induction on n. And we have a base step n equals 1, which is trivial. How many ways are there to factor 1? Just 1, and that's it. And, well, then we take the induction step, take a natural number, and assume that uniqueness of the prime factorization has been proved for all m between 2 and n minus 1. If n is a prime number, there's nothing to be proved, because prime numbers can be only factored one way. That's the definition. So now we let n be a composite number, and we suppose for a contradiction that there are prime numbers p1 through pk and exponents q1 through qk, so that n is the product j equals 1 to k pj to the qj, as well as, and those should all be distinct prime numbers, p1 hat through pk hat to p hat sub k hat, and exponents q hat 1 through q hat k hat in the natural numbers, so that n is the product j equals 1 to k hat of the pj hat raised to the qj hat. So that would be two different prime factorizations. Because p1 divides n, which is the product j equals 1 to k hat of p hat sub j to q hat sub j, p1 must divide one of the pj hat. That was that lemma, that if a prime number divides a product, it must divide one of the factors, and so that means that p1 must be one of the pj hats, and we can assume without loss of generality that p1 is p1 hat. Then, well, then p1 hat, which is p1 to the q1 minus 1 sum, product j equals 2 to k, pj to the qj, well, that's p1 to p1 times p1 to the q1 minus 1, product j equals 2 to k, pj to the qj, which is the first possible factorization of n. which is equal to the second factorization, product j equals 1 to k hat pj hat to qj hat, which is, if I split off the first one, p1 hat to q1 hat minus 1, product j equals 2 to k hat pj hat to the qj hat. And if we cancel the p1 hat, then that implies that p1 to the q1 minus 1 product j equals 2 to k pj to the qj is pj p1 hat q1 hat minus 1 to product j equals 2 k hat pj hat to the qj hat. Man, that is harder to say than to read, I think. And those numbers are smaller than n and bigger than 2, which means by induction hypothesis, these two factorizations must be the same. That is, p1 must be p1 hat, q1 must be q1 hat, k is k hat, and there's a bijective function that scrambles the numbers 2 through k, so that for every j between 2 and k, we have that pj is p sigma j hat and qj is q sigma j hat, which just basically means that all the factors here are the same as over here. They just are scrambled and they occur with the same exponents. Whoa, okay, let's prove a quick corollary here. If we have three positive integers a, b, and c, so that the greatest common divisor of a and b is 1, and so that a divides b times c, well, then we must have that a divides c. Proof, well, we take a prime factor of a, and we let k be the exponent with which p occurs in the prime factorization of a. Because the greatest common divisor of a and b is 1, we have that p does not divide b, and because p divides b times c, that means that p divides b times c, that means that p divides c, so p must be a prime factor of c. And it must have an exponent of at least k in the prime factorization of c, and that's a quick induction where you repeatedly just divide factors p off of c and keep using the fact that a divides b times, or a over p divides b times the c with the other factors divided off. And because p was up, and so that is something that I deliberately leave to you as an exercise so that you can fully understand that part of the proof. And because p was arbitrary, the whole prime factorization of a must therefore be a subproduct of the prime factorization of c, right? Every p to the k that occurs in the factorization of a will also occur in the factorization of c. And that means that a divides c, and that's what we wanted to prove. Now we can talk about least common multiples and greatest common divisors. We take m and n, and we let those be integers. The greatest common divisor of m and n is the largest divisor d, so that d divides m and d divides n. The lowest common multiple of m and n is the smallest d, so that m divides d and n divides d. And the theorem is that if m and n are natural numbers, and p1 through pk are the prime numbers that occur in the prime factorizations of m and n, well, then m is the product, and if m is the product pj a to the j and n is the product pj b to the j, where aj and bj could be 0 too, so basically we want to have the same factors, and if there is a factor in n that doesn't occur in m, then the corresponding aj is just set equal to 0. Well, then we have that the greatest common divisor of m and n is the product j equals 1 to k p to the minimum aj bj, which in particular then proves that the greatest common divisor exists. Now that is it feels slightly like circular reasoning because we already used the greatest common divisor in the previous result, but basically to check whether something has greatest common divisor 1, well, I could just write down the prime factorizations which exist and check if they have any common prime numbers, right? So this one now fully establishes that the greatest common divisor exists. The lowest common multiple, mn, is the product of the pj to the maximum of the aj bj, and m times n actually is the product of the greatest common divisor with the lowest common multiple. We're going to prove only parts 1 and 3. For part 1, note that the product j equals 1 to k pj to the minimum aj bj clearly divides both numbers m and n. And if now d divides both m and n, Then the prime factors of D must be among the P1 through Pk, because those are all the prime numbers that go into M or N. And that means that D is the product J equals 1 to K Pj to the Cj, because that's its prime factorization with potentially some Cj's equals 0 thrown in. And if any of the Cj's was greater than the minimum of Aj and Bj, well then D would be divisible by a higher power of Pj than M or N. And that can't be. And so that means for all j equals 1 to k, we have that Cj is smaller or equal than the minimum of Aj and Bj. And that means that D as the product of the Pj to the Cj is smaller or equal than the product of the Pj raised to the minimum Aj, Bj. And that means that the greatest common divisor is the product of the Pj's raised to the minimum of the Aj, Bj. For part 3, we actually only have to prove that for all real numbers x and y, we have that maximum x and y plus minimum of x and y is x plus y, because that's what we would do, right? We would take the lowest common multiple multiplied with the greatest common divisor, which means we have to add the corresponding exponents, and the exponents we ought to get should be the sum of the exponents that we get from the product m times n. And for case x less than or equal than y, we have the following. We have that the maximum of x plus y plus the minimum of x plus y. Well, that would be the maximum is y and the minimum is x. And that means that the sum is x plus y. And the case x greater than y is, of course, similar. And that finishes the proof. Okay, now we're looking at another lemma here. If we have two positive integers and d is a divisor of m times n, then there are positive integers dm and dn, so that d splits into dm times dn, where dm divides m and dn divides n. Now those are not necessarily unique anymore, because there could be several ways to split it, but at least there is a way to split d. Conversely, if dm divides m and dn divides n, well then of course dn divides m times n. That's quite trivial actually. So let d have a prime factorization, product j equals 1 to k pj to the aj, and we will always assume that the pj and the prime factorization are distinct, so if I don't always mention that, that's already part of what I'm saying here with the prime factorization. Let dm be the product j equals 1 to k pj to the bj, where bj is less than or equal than aj, and it's the largest possible exponent, so that pj to the bj divides n. And let dn to be the product of the pj to the aj minus bj. Well, that presumably is the product, because, well, if I take dn times dm, I of course get the product of the pj to the aj, so I get d. What else do I have? I have bj is the largest possible exponent, so that pj to the bj divides n, so that means that this product definitely divides n. Divides, that should be an m here, I believe. Yes, sorry about the typo. That is supposed to be an m. And so let's see, if all those pj to the bj divide m, then because the pj's are pairwise distinct, we certainly have that d sub m divides m. And we have already said that dm times dn is d. Well, if dn now did not divide n, then there would be one of these powers that doesn't divide n, but that extra prime factor, that extra pj, could not be pushed into m, because we have already pushed as many powers as possible into the m, and so that would be a contradiction, which means therefore that dn must also divide n. Here's where my sometimes rather terse proofwriting style is catching up with me a little bit, but that's exactly what makes you think, and of course part of this presentation is also to make you think. Okay, and the converse is quite trivial, right? I mean, if dm divides m and dn divides n, then the product divides m times n. Yeah, sure. Okay, so we can now prove another lemma. We're going to say something about prime numbers in the next theorem. If we have two integers a and b of the form 4k plus 1, then a times b is of this form too, and this one will be refreshingly simple to prove, because if a is 4m plus 1 and b is 4n plus 1, then a times b is 4m plus 1 times 4n plus 1. You multiply that out, you get 16mn plus 4m plus 4n plus 1. And that's, of course, 4 times this thing here plus 1. And that is the proof already, because AB now is of the form 4 times number plus 1. And with that, we're going to prove a special case of Dirichlet's theorem, which is that there are infinitely many prime numbers of the form 4k plus 3. Well, we already know that all but one prime number are odd, and there are two kinds of odd numbers. There are odd numbers of the form 4k plus 3, and there are odd numbers of the form 4k plus 1. Well, we're showing here that there are infinitely many prime numbers of the form 4k plus 3. Alright, the proof is, well, suppose for a contradiction that there are only finitely many prime numbers of the form 4n plus 3. Well, we call them p1 through pn, and so that n would probably look better as a k. And now it is a k. Well, that wasn't even a mistake, because technically I'm free to use any letter I want here as a dummy variable, but it wasn't pretty. Okay, so these finitely many prime numbers of the form 4k plus 3, we call them p1 through pn, and we let x to be the product of those numbers. Well, then x first of all is odd, because those are all odd numbers. And one of x plus 2 and x plus 4 is of the form 4k plus 3, because two consecutive odd numbers are either 4k plus 1, 4k plus 3, or they are 4k plus 3, 4k plus 1. Okay, so let y be the number among x plus 2 and x plus 4 that is of the form 4k plus 3. Then none of p1 through pn divides y, right? And that is because none of those odd numbers divides 2 or 4. And by the preceding lemma, some prime of the form 4k plus 3 must divide y, because if all the prime factors of y were of the form 4k plus 1, then y itself would be equal to 4m plus 1 for some number. And that's a contradiction, because, well, if none of p1 through pn divides y, but at the same time some prime number of the form 4k plus 3 must divide it, well, then one of the p1 through pn would have to divide y at the same time. It can't, so that's a contradiction. And that proves this special case of Dirichlet's theorem. So we can see here that as we have learned that prime numbers are what all numbers are built up from, which is the fundamental theorem of arithmetic, we can also now say a few things about prime numbers. Not only are there infinitely many of them, there are infinitely many of the form 4k plus 3. Okay, now we're on the home stretch. We're going to talk about roots. And first of all, we again need a few results about integers. If a and b are integers with greatest common divisor d, then the greatest common divisor of a divided by d and b divided by d is 1. The proof for that is, well, suppose for a contradiction that the greatest common divisor of these quotients is x greater than 1. Well, then a is equal to m times d times x, because, well, a is divisible by d, so it is some number times d, and that number then is m times x. Similarly, b is divisible by d, so d is some number times x, and that number is, of course, the b over d, and if that is n times x, well, then I've got that. And, well, that means that dx, which is greater than d, is a common divisor of a and b, and that's a contradiction. Note that this result means that rational numbers can be written in lowest terms, which means now we could, for example, look back at the proof that there is no rational number r so that r squared is equal to 2, and now we can basically do the same proof that we have done in an earlier presentation already, but now everything is fully justified. So if we let n element n be so that n squared equals 2z for some z element n, then 2 is a factor in the prime factorization of n squared. But every factor in the prime factorization occurs with an even exponent, which means n squared is 2 squared k squared for some k, which means that n is equal to 2k, and that means if n squared is divisible by 2, then so is n. And now we can suppose for a contradiction that there is an integer z and a natural number, an integer n and a natural number d, so that n over d squared is 2. We can assume that they have no common factors and that n is a natural number. N squared equals 2, d squared implies n equals n2 times 2. So 2d squared is n2 times 2 quantity squared, which means that d squared is n2 squared times 2, which means that d has a factor 2, and that means 2 divides n and 2 divides d, and that's the contradiction that we wanted to have. So this proof is not new, but now in every single step we have that everything is justified, because we know now that there is a prime factorization, and we also now know that we can write quotients in lowest common terms, right? So if we were to build a theory, then this theorem would really come, this proposition would come now, and it wouldn't have been mentioned in the earlier presentation, where we had put some disclaimers in. Okay, so now, finally, let's take a look at a polynomial where the leading coefficient is 1, and then we've got more coefficients cn minus 1 through c0. The coefficients are integers. If alpha is a root of p, then alpha is either an integer or an irrational number. Well, proof is by contradiction. So, suppose for a contradiction that there is a u that is an integer and a d that is a natural number, so that p of u over d is 0 and d is greater than 1, and u absolute value and d are in lowest common terms. Well, then 0 is equal to p of u over d, which is u over d to the n, plus cn minus 1 u over d to the n minus 1, all the way through c1 u over d plus c0, and I can multiply that with d to the n minus 1, I think, so that would mean that 0 is u to the n over d, plus cn minus 1 u to the n minus 1, plus cn minus 2 u to the n minus 2 times d all the way through c1 u to the dn minus 1, because 1d cancelled, and c0 d to the n minus 1. But realize now that this sum back here, that's an integer, right? And an integer plus a fraction equals 0, that means that the last fractions is also an integer. So because all but the first summand are already guaranteed to be integers, we must have that d divides u to the n, and that means that d and u absolute value have greatest common divisor greater than 1, and that is a contradiction. And so that means that these roots must either be integers or irrational numbers. Now, real quick, we have to be careful here. In this preceding result, the leading coefficient must be 1, because if we look at the polynomial 9x squared minus 4, that also has integer coefficients, well, yeah, then x equals 2/3 is a solution or is a root, because 9 times 2/3 squared would be 9 times 4 over 9, which is 4 minus 4 is 0. And that means that in this theorem that we just had, we must have that the leading coefficient must be 1, and that is what I wanted to show here. Okay, I've been talking quite a while. I'm certainly fading a little bit. I'm not going to record another presentation today. If you're tired right now, I don't blame you. I required you to certainly keep up with quite a few details in the proof of the fundamental theorem of arithmetic, which I think we finished off nicely. And then we had a couple of hiccups in the slides. I apologize for those, but I think we got through those also, and we've got good proofs what we need to look at, for what we needed to look at. And so now I'd suggest you take a break if you feel like it. Go ahead and hit some homework problems, have some fun. I'll see you in the next presentation.